All right. Okay. Thank you so much, everyone, for joining in. I'm super excited to be presenting at the HPC Day, and I'm Shivay. Unfortunately, my co-speaker Rishit could not make it because of visa issues, but we have recorded some of his part of the talk. So yeah, I hope that all of you enjoy. So the main purpose of today's talk is really to understand that how can you leverage the use of GPUs inside of Kubernetes clusters, but primarily for machine learning workloads, and how you can maximize the efficiency of these GPUs for your machine learning workloads. Because as we know that as the model size of machine learning models becomes bigger, as you have more amount of training data that you work with, the training process and the overall complexity for the training process does increase quite a bit, right? So we need to use things like GPUs or TPUs. And if you were to scale this or orchestrate this inside of a Kubernetes cluster, how can you do that? And what are some of the best ways of being able to do so? And use of these GPUs inside of container orchestration technologies, specifically fine-tuned for machine learning purposes, such as Kubeflow and Flight. So this is what is the broad agenda for today. So just a quick introduction. I'm Shivay. I'm a developer relations engineer at Millisearch, and Rishit, who is my co-speaker, he's a CS undergrad at University of Toronto. Now, I'll just take a quick fire of what exactly is MLOps, right? So whenever we talk about any machine learning lifecycle, there is always, we start with defining the problem statement, talking about the training data set, then we train our machine learning algorithm, we fine tune it, and we get the results. And if the results are good enough, we'll go ahead and deploy it, right? So this is, of course, our typical machine learning lifecycle. But if we talk about the entire process of MLOps, which is basically bringing in DevOps for your machine learning workloads, we see that the ML code, right, that is a very small part of the overall architecture. And of course, the most important one that I feel personally is the serving infrastructure. Because if you're running major deep learning models, if you're running large deep learning models, you'll need a lot of compute power. And how can you effectively and efficiently use that compute power really relies on how well optimized is your serving infrastructure. And that is what we are going to be covering in today's session. Now, of course, talking about the primary hardware that is used to run your machine learning tasks. So we start with CPUs. And then, of course, if you have more compute-intensive tasks, then GPUs are a great way to be able to, which are, of course, more optimized for compute-intensive tasks. So especially, let's see if you're running a lot of deep learning machine learning models, then GPUs. And, of course, TPUs, which are tensor processing units, are more optimized for those workloads. So as you work with major models, with larger models, you will primarily use a combination of either of CPU, GPU, and TPUs. But of course, as we understand that, let's say if you were to compare between running your machine learning workloads with just two CPUs or with, let's say, a CPU and a GPU, you may think that since GPUs are more optimized, it might be better to just run your machine learning workloads with a CPU and a GPU as compared to just running it with two CPUs. But there are some challenges when it comes to choosing the right kind of configuration of your hardware to run these machine learning models. And that's where I'll just quickly play this video, which is recorded by my co-speaker, Rishit. Hopefully the audio comes through.
So I want to talk a bit about why adding a GPU is not the same as adding a CPU, and it requires fundamentally changing a lot of your code. Often this is handled by frameworks under the hood for you, but sometimes it can require still changing a lot of code or better scheduling jobs, as I like to say. And yeah, so that is what I want to show you why adding one GPU is not the same as just adding one CPU in terms of how you run the code and what kind of strategies work best. So instead of showing this in some theoretical way, let's go ahead and do an experiment. So for our experiment, at this moment, let's just assume we have no XLA, we have no gradient accumulation. And if you don't know what this means, that's fine. We're not using it at the moment. At the end, we'll introduce this and also see like how it can help, especially for GPUs. But at this moment, let's just focus on what we have at the one GPU plus one CPU and two CPUs. Great. So now we want to train a machine learning model. So I'll just take ResNet 50, one of the most popular models out there. And what I want to do is I want to load the data. This will be quite expensive because my experiments are on ImageNet. And I want to pre-process the data. This would, if I think about it, this would be a bottleneck on the CPU. I'll probably copy the tensors to GPU. So that will be a bottleneck on the PCIe. And for training, I'll probably use the GPU in the GPU setting. Great. So this is our experiment. And let's see, what do we run? So we run all these steps. Open is just load the data, read the data, preprocess, and then train the data. This is what our current way of running it looks like. And this just makes sense, right? So you first open an image, you preprocess the image, then you train on the image. And this makes a lot of sense. So this kind of profiling looks good to me. And this works fantastic on CPU because each of these steps can be individually run with two CPUs, and you get quite some speed up running each of these individual steps with two CPUs. So this runs fantastic on CPU, and this also is pretty easy. But let's try doing the same thing on a GPU. And my first guess is the parts where my model is loading the data and reading the data won't work so well having a one GPU plus one CPU setup. But the training the model part would probably be faster than two CPUs with a GPU. Great. So let's see some numbers. And for the one GPU, I have a Tesla T4, and I'll compare this with two CPUs. So just running it in the naive way for a single epoch on ResNet 50, I see two CPUs are faster than having one CPU and one GPU. That definitely does not seem intuitive. You just added a GPU, which is a lot more costly, and you end up slowing down your process. So I just wanted to show you that this is not the same. And if you think a bit about this, then you have a lot of this idle time where the GPU is waiting for the CPU. Yes, your train steps, the ones in the red, do get smaller. These get considerably smaller. But there is a lot of time where the GPU is waiting for the CPU. And that part gets considerably larger now that you only have a single CPU. All right, and of course, if you have like a big enough model, this strategy might work out just way too well. But we'll talk more about why this happens and how you can tackle it.
Yeah, so what we kind of covered over here was that you saw that when we used like two CPUs, the performance was better. And that is primarily because that a lot of times our GPU was just waiting for the system resources, right? So as we uncover some of the strategies of making this more effective, we'll see that how can we configure our hardware in such a way and provision the hardware at runtime to make these processes more efficient. Now, of course, coming back to the next point, what's more related to today's topic is how can we make the use of GPUs in Kubernetes. So this is just a bit of a primer for those who might not have probably configured. So by default, Kubernetes does support stable release for supporting your GPUs, and these GPUs can be run on your individual nodes, and primarily whether it's your NVIDIA-based or AMD-based GPUs, they can be run across multiple nodes inside of your Kubernetes cluster. And it's very easy to just set it up. You just have this particular configuration that you can set up as part of like your device plugin that allows your pod to access your specific hardware resources for Kubernetes. So if you were to use, let's say, AKS, GKE, any other cloud provider, or even run this locally, so you'll just have to set up the particular agent inside of your node to be able to access your particular hardware. And of course, as I mentioned that when it comes to handling a lot of these compute-intensive tasks, the most important aspect is that how can we effectively utilize these resources, right? These GPUs and these TPUs in a more effective manner. Now, when you have a very large workload, right, a very large machine learning workload, you might not just be able to have one particular GPU for your task, and you might be required to use multiple GPUs or a combination of multiple GPUs and TPUs. So there are some issues, inherent issues that come when you are handling multiple GPUs. So the first one is memory, right? So as you basically have your entire data and you split your data across these multiple GPUs, so a lot of issues might arise with respect to arranging the memory and how the memory is being shared between these GPUs and the TPUs as they are processing your data. And similarly, like when it comes to synchronization of these particular GPUs and TPUs and seeing that how the model evaluation is being done across these multiple devices, how to manage them effectively is also a big issue that we have to face, right? And similarly with load balancing, that how are you distributing your entire data load across these multiple devices, right? And similarly for debugging as well, if you face certain errors when it comes to some of the models not running properly, so how can you effectively debug which particular GPU is causing that particular issue? So these are some of the inherent issues that comes when we are dealing with multiple GPUs and TPUs. But there is a way to be able to resolve most of these issues, right? And that's where parallelism really comes into picture. So the entire concept of parallelism is that you are taking either your data or your hardware resources and dividing them into parallel tasks, right? Very similar to how we have parallel processing inside of our CPUs. We are bringing in those same principles, but for being able to do our machine learning evaluation. So primarily, if you talk about data parallelism, we are essentially splitting our data across into different shards, right? Similar to how we have database sharding. And then we are taking each of these data shards and running them in parallel GPUs. Now, the great thing about data parallelism is that each and every GPU has the context for your entire model, right? So as the model evaluation gets done, each and every GPU has the context for the entire model. And at the end of the evaluation, once the metrics have been generated, you kind of back propagate all of these metrics into one single source so that then you can get insights of how the model training basically went. But in comparison to this, we also have the model parallelism, where basically you don't break your data, but you basically break your entire model into different fragments, and you are running them, right? Very similar to how the data parallelism takes place. So one of the examples is a tensor parallelism, where you are taking your main model and breaking them down into individual tensors, and then each of these tensors are being associated with the GPUs, and as the processing takes place, we again have the context, and we are able to very effectively manage our resources. So the idea is that together with the data parallelism and the model parallelism, that includes like tensor parallelism and pipeline parallelism, we're effectively able to maximize the use of multiple GPUs or TPUs in order to improve the machine learning performance, because we're effectively breaking down our entire spectrum of our data and our model itself, and still being able to use techniques like back propagation to be able to fine-tune our results at once. And now what we'll see is that how can you use these techniques with your GPUs and inside of a Kubeflow or with Flight. So now I'll head back to a pre-recorded demo from my co-speaker, Rishit, who kind of goes further into how do we actually enable data parallelism and pipeline parallelism inside of our GPUs.
Okay, so now that we know about parallelism, let's do another experiment. And this time I'll walk you through how you would run your models better on GPUs and probably run them faster, because the last results where I added a GPU and the model started running slower. The overall training process started happening a lot more slower. So I probably don't want that. And let's see how we do this. So again, we come to the experimentation part. I again have a Tesla T4. I again have two vCPUs, and the Tesla T4 only has one CPU. So that is the setup I have. And the way I do this is just for fairness. All of the experiments I was talking about and the one I do over here right now are on a single machine. So I have a single machine with two CPUs and one GPU. And whenever I try it out for two CPUs part, I explicitly make sure not to use the GPU and likewise. So I do this with code, and that allows me to get fairer results. And I also make sure that none of the computational graphs are being cached or anything. So okay, enough of that. But what we want to do is probably use some kind of GPU strategy. And I did some GPU strategy, which worked out way too well. The time was reduced by quite a lot. And other things I want you to notice is that the overall epoch time was not only reduced, but the training part is faster on a GPU. And the secret sauce to making this faster on a GPU, or how this happens, is scheduling my process and my code in such a way that there's very little time for which the GPU is idle. So over here, if I see in an epoch, there is very little time for which the GPU is idle compared to our previous attempt. And compared to our previous attempt, where we just loaded the data, read the data, pre-processed the data, and trained it sequentially, which seemed to work pretty well on two CPUs. Great. So how do you do this? So how do you do the training with having very less GPU time, very less GPU idle time? So I'll talk about a few strategies to do that. And the first secret sauce to doing this is prefetching prefetching the tensors in memory. So what I probably understand is the reason the GPU was waiting for the CPU was because it did not have pre-processed data ready on which it could train the model. So the way you do this is every time, every time a model is running nth epoch, the CPU at that moment is trying to load the data, read the data, pre-process the data for the n+1th epoch. And and this is pretty interesting because when the GPU actually gets to training the model on the next batch, it already has data ready for it, and which is why there are no GPU idle times after every pre-process step or while every read step. Another difference I notice is that the pre-process steps are that the pre-process and read steps do not happen sequentially, and and this is pretty important to for our GPU strategy as well, because we want the pre-process code to be ready when the GPU is idle. So and the way we do this is pretty simple. Just use vectorization. So I read for the whole batch at once, and then I just run pre-processing steps. So so while the first pre-process is being run, so while some pre-process is being running, I'm preparing for the next set of data. The GPU is running on the previous set of data. So that is how this is facilitated. And if you see the reason why the open and read on why the open read and pre-process, some part of it also happens in parallel is because of parallelized data extraction, which is another secret sauce. So so we took out the secret sauce which which allow us to get to very little GPU idle time as possible. And this seems to work pretty well for one GPU and one CPU. And let's see the results for this. So if we see the results for this, I have two vCPUs taking about the same time. So this takes about the same time as earlier, because there is not a lot changed when you're trying to do this on a CPU. The train time pretty much remains the same, and you're just changing when each job is happening. So this improves the CPU time by a very small margin. But if you see the GPU time, this has improved by quite a huge margin. And that is because if you see the profiling graph again, you see that this time around, the time it takes for the GPU to train on the data is a new bottleneck. So the bottleneck is no longer how much time the CPU take to pre-process the data or load the data. The bottleneck now to make epochs smaller.
Just to keep for the time's sake, I'll just probably skip over this part. But the idea of what you saw over here is that as soon as we added the data parallelism, we saw that now the GPU was no longer staying idle. So really the trick that we wanted to showcase over here is the dynamic allocation of GPUs at runtime when you're processing your data, right? So that's the main secret sauce when it comes to being able to make more efficient use of these GPUs. And at the end, what my co-speaker is primarily presenting is that when you have, let's say, more than one GPU as well, then you can use like distributed data parallelism so that it can be spread across these multiple GPUs. And you can, of course, then leverage these different types of parallelism techniques in order to do so. And going
Okay,
forward,
so now that we know about
so of course, as we mentioned, right, that if you have like, let's say, multiple nodes as well inside of your Kubernetes cluster, so this will be primarily focused towards Kubeflow. That whether you want to use like, let's say, a TensorFlow based model, so you could use like keras model.fit, or you could basically see all these different types of techniques, right? So you see mirrored strategy, TPU strategy, central storage strategy. So these are all the different strategies that you can actually apply to your Kubeflow cluster with the help of this parallelism technique, so that it can make it more efficient for your Kubeflow to be able to do the multiple parallelism if you are running these multiple GPU clusters. And probably if we can just have the last like 5 minutes, we just have one Kubeflow demo that we like to just demonstrate quickly. So this is a demo.
So with that, let's move on to the demo. And I'll be showing a demo using of using all the strategies you talked about of using multi-GPU, multiple GPUs spread across multiple nodes for our jobs. So I have a lot of moving parts over here, and I'll just start by giving a brief background about what the experiment setup is. And so I have a Kubeflow cluster, and this Kubeflow cluster also has two GPUs. These are two Tesla A100 GPUs, and this is again very similar to the setup I use for my own research or what I use for often training on multiple GPUs. So okay, but let's start by seeing the config file I have. So since this is Kubeflow, I have a config file to do multiple benchmarks, and so this is structured as a TensorFlow job, and a lot of the benchmarking code. So a lot of the original benchmarking code of taking a model and running it is actually borrowed from TensorFlow benchmarks, the official TensorFlow benchmarks repository. So we'll use much of that. I've slightly modified the code to parse out and prettify the logs, so I can share it to you as proper benchmarks. But so this is what we'll be doing at the moment. Let's go ahead and run two jobs. Two jobs will also take quite some while to run. So, but I'll show two jobs. So I'll train a ResNet 50 model on the ImageNet dataset, once with the parameter server strategy. And so once I do it with the parameter server strategy, which is a type of data parallelism, so I'll do it once with the data parallelism. And then I'll use the replicated strategy where you have all the tensors in one central place, and then you just copy them to GPUs as needed. So these are the strategies I'll be trying out. And as I was talking, this takes quite some time. But since this is a TensorFlow job, you can directly run it with Kubernetes, just this YAML, and of course the code to create the CNN architecture. So all of that was present in TF-CNN benchmark. So I already have that, and this takes quite some while. So I've already run this in Kubeflow, and particularly what I wanted to show you was the results. And so actually, let's see the results first. And since it's a TensorFlow job, you could most certainly just go ahead and run this in Kubeflow. But so these are the past results, and as I was saying, this takes quite some time because this loads the ImageNet dataset, which is quite a few million images. It has to run this model on. So we take the ImageNet dataset, use some augmentations on it, and then what I want to see is especially this metric, total images per second. So think of this metric as just how many images the GPU can train on per second. And the model itself is pretty simple, just a ResNet 50. But I just wanted to show this benchmark. And this is again same to the benchmarks I was working on earlier, our experimental setup earlier. And I had actually prepared those benchmarks in this environment, making few changes here and there. So that was for the parameter server, and then we see the replicated one. So since this is a small model, since it's a particularly small model, I see that changing, and also because this is just two GPUs, so changing whether the tensors live in a central place and are then copied to GPUs uh, would not have a big effect on the PCIe bus. And thus, as we were expecting, it took about the same time for both these strategies. But that's a quick overview of how you can with that, let's.
So just to kind of summarize what happened was that we showcased two different strategies of being able to use two GPUs with Kubeflow, and we ran these two strategies on a ImageNet dataset, and you can see ImageNet model, and you could see the results, right? So another way that you can actually configure your GPUs is with Flight. So Flight is basically a Kubernetes native workflow automation system for both data and for machine learning processes. And you can very easily configure your GPUs for being able to run your machine learning workloads as these tasks that are embedded inside of these workflows. And you can very easily just set up by using plugins where you're setting up these GPUs and you're giving them access to the pods which are running these flight workloads. So whether you're using Kubeflow or using Flight, there is support for GPUs for both, and you can leverage these strategies that we spoke about, like for your data parallelism and your tensor parallelism in case of both Kubeflow and also for Flight. With that, we'll be open to questions now. Thank you so much, and yeah, I hope that you enjoyed the presentation.